Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So what we are going to do today is we'll prove the following result. So let me state the result first and then I'll talk a little more about it. So we'll prove the following theorem by due to Allender and Hartramp. So this was shown in 89. So every language in uniform AC0 can be accepted by a uniform family of depth 3 threshold circuits of size quasi-polynomial. So n to the power log to the power some constant times n. Okay, so essentially what this is saying, and let me just mention what we mean by threshold circuit. So a threshold circuit takes as input x1 up to xn and x1 calculate it as bar, x1 bar up to xn bar, and constants 0 and 1, and consists of majority gates. Okay, so majority gate is something that we have seen. It outputs 1 if more than half the number of inputs are 1. Okay, so essentially what this theorem is saying is that you take a arbitrary but constant depth circuit consisting of arbitrary fan-in and an OR gates. Okay, so this AC0 circuit can have any depth d, and we actually reduce the depth to 3, but the thing is that, so we reduce it to a depth 3 threshold circuit. So the circuit will now have majority gates and size quasi-polynomial. Okay, and the important thing about this construction is that this is a constructive proof, in the sense that we get a uniform family of depth 3 threshold circuit. Okay, so essentially what we will show is that these circuit classes that these circuits that we will be generating can actually be constructed. Okay, so one more point. So the kind of uniformity that we consider over here is polylog space uniformity. So we will be considering polylog space. Okay, so there is a polylog space Turing machine which given n can produce that circuit. Okay. So there was actually a result prior to this again due to Allender, who gave a non-uniform proof of this result. Okay, so Allender had shown earlier that there exists a family of circuits, a family of depth 3 threshold circuit which can actually do the same thing, but it was not constructive in nature. Okay, so what those circuits are was not known. So later on he along with Hertramp improved that result and showed that actually you can get a constructive proof as well. Okay. So this is what we are going to see, and the reason why this proof is very interesting is because it it uses linear algebraic techniques. It shows that we can actually represent circuits as a type of polynomials, okay, over GF2, well, approximated as a type of polynomials over GF2, and then using those polynomials we will reduce the depth, and it uses a very famous result again in complexity due to Valiant and Vazirani, which again we are going to see today. Okay. So, okay. So, one more point that I need to mention is, so all arithmetic computations that we will use are modulo 2. Okay, so I won't be mentioning modulo 2 each and every time. So for the rest of this discussion, we will just assume this. Okay. So how does the proof go about? Okay. So essentially, what we will do is we will let's say we will look at a OR gate. Okay, so suppose I have a unbounded fan in OR gate, and then we will show that actually I can replace this OR gate with the depth 2 circuit, okay, where the top gate is a parity gate, and at the next layer we have some AND gates. Okay, we have some polylog many AND gates, and these kind of circuits can actually be represented as a polynomial over GF2. Okay, it can be represented, we will see how it can be represented. In fact, it is easy to see how it can be represented as a polynomial. In fact, it is a polynomial of the form sigma pi, because the AND gates can be thought of as product of the incoming variables or incoming gates, and the parity gate at the top is basically a sum gate, because we are doing modulo 2, therefore parity is just the same as sum. Okay. So any OR gate essentially can be converted to a polynomial of the type sigma pi. Okay, and this will not be an exact computation, this will be a approximate computation. We will see that we will define a probabilistic circuit, and we will show that any OR gate can be converted to this sigma pi type of polynomial with high probability. Okay, so which gives a correct answer with high probability, and we will do the same, and the same thing can actually be said for AND gates as well. So now for OR and AND gates we have these approximation. So now we will combine them and we will show that any circuit can be squashed down to depth 2. Okay. So okay, so yeah, any circuit can be squashed down to depth 2. Now why this depth 3 is coming over here, we will discuss that later on. I mean, why we need additional layering over here, but that is trivial. Okay, so next let me define probabilistic circuit. So probabilistic circuit is actually quite easy. So a probabilistic circuit C accepts a language L subset of 0 1 to the power n. So, we are looking at all strings of length n if for all x in 0 1 to the power n, if x is in L, then probability that C of x accepts is greater than 3/4, and if x is not in L, probability that C of x accepts is less than 1/4. Okay, so this is again also what is called a two-sided error circuit, and this probability is over the choice of random string. Okay, so this circuit, in addition to its input x, okay, so we have some part which has the input x, and then we have some random bits that this circuit takes. Okay, and this probability is over all choices of this random string. Okay, so how many random bits are used and things such as that kind of will be a parameter for us. Okay, so what is the size of this random string? And although for generality I am defining probability circuits which can have two-sided error, but actually we will not be considering two-sided error, we will only be looking at one-sided error. Okay, so if x is not in L for us, the circuit will always give the correct answer, and if x is in L, it will give the correct answer for 3/4 fraction of the random strings. That is what we will be doing for our purpose. Okay. So, anything else? Okay. So, now let me define the or not define, let me state the theorem due to Valiant and Vazirani that we will be using, and in fact this is the main ingredient of this proof. Okay, so let's give these some names. So let me call this as theorem 1, let's call this as theorem 2. So let S be a, okay, so let M be greater than or equal to 1 and S subset of 0 1 to the power m be a non-empty set. Okay, let W1 up to Wm be m bit vectors chosen independently and randomly. Okay, let S0 be equal to S and Si be all vectors in S such that V dot W1 equals V dot W2 equal to V dot Wi equal to 0, then uh, the probability that there exists an I less than m such that S of I has a single vector is high, is greater than 1/4. This is what we will be using. Okay. So, what is the so what is this theorem saying? This is saying that you take some non-empty subset of vectors. S can have any size. Now, what I will do is that in a sequential manner, I will be building these sets S1, S2 up to S of m, such that what I do at each step is that I reduce the number of vectors in S. So each Si, the size of each Si progressively potentially reduces. How does it reduce? So I will essentially remove all vectors which are orthogonal to a specific Wi. So whenever I am considering S1, I will remove all vectors that are orthogonal to W1. Then when I look at S2, I will remove all vectors that are orthogonal to W1 as well as W2, and so on. So I keep on removing this. Now what Valiant and Vazirani showed is that at some point, so before I reach, or by the time I reach m, there will be some I such that the number of vectors that would remain is exactly equal to 1. So, and how is this result used? So, using this result we will prove the following result, and this is going to be the crux of our main result. So, for all R, there is a uniform family of depth two circuits of what are the parameters of size n to the power log to the power O1 of n. So actually this O1 also can be fixed. I think it is 3 or 4, something of that order, but yeah, it's a constant of size n to the power this, having let me say uniform family of probabilistic depth to circuits. So probabilistic depth to circuits of size this much using order log cube n random bits for all R. There is a uniform family of probabilistic depth to circuits of size polylog using log cube n random bits that computes the OR function with error at most 1 over n to the power r. And moreover, circuit has a parity gate at the top and AND gates below it having fan-in order log to the power 4n. Okay, so essentially what we are saying is that we take a, suppose I have a OR gate, okay, which is taking some n inputs. So I can replace this with the following circuit. So I have a parity gate and then I have some AND gates, and the size of this is polylog. So this is some n to the power log to the power O1 of n, and these AND gates have fan-in order log to the power of n, and this computes the circuit, this computes the OR function with error at most 1 over n to the power r, and r is for any r, so we can choose r as we want. Okay, so what is the idea? How, so once we prove this, essentially it's easy to see how the result will follow. We'll come to that later on. But what is the idea? How do we go about proving this lemma using this theorem of Valiant-Vazirani? Okay, so what we show is that well, so if I take the OR function, okay, so if all the inputs are 0, then of course the OR is 0, and if some of the inputs are 1, then the OR function gives a output 1. Okay, so now instead of instead of saying that sum of the inputs 1, we will use this result and we'll convert this into a circuit where exactly one of the inputs will be 1. Okay, so we'll set S to be the set of all those xi's which are 1. Okay, so suppose the OR gate evaluates to 1, it means that there exists at least one input which is 1. Okay, we don't know how many of them are there, but there is at least one. So we'll set S to be those inputs which are 1. Okay, so now we can see by this result that it satisfies our hypothesis, that is S is non-empty, there is at least one of it which is 1, and these Wi's will be the random bits that this circuit will kind of use, and then we will do the construction in an appropriate manner, so that in some m steps, okay, in some m is actually will be log n for us, we will actually be coming to a point where there is exactly one input which is 1. Okay, so now on one side if the OR is 0, then there are 0 inputs which are 1, and on the other side if the OR is 1, then there is exactly one input which is 1 with high probability, of course. Okay, and then we will show that I can actually do some simple arithmetic flipping. So basically I have a parity gate, so now it is easy to see that if I have a parity gate and if there is exactly one which is 1, then the parity will output a 1, and if all of them are 0, then it will output a 0. Okay, so we'll come to that. Okay, so it's not hard to see. Okay, so again, so looking at it in a different way, so suppose if I just try to approximate a OR gate using a parity gate. Okay, so forget about everything else. Okay, so suppose if I just replace this OR with a parity, what is the problem? The problem is that if there are an even number of inputs which are 1, even then the parity will output 0. Okay, So if everything is 0, then of course the parity is outputting 0, which is what we want. But if there are even number of 1s, I want the circuit to output a 1, but that is not what the parity gate would do. The parity gate would output a 1, and that would happen for a lot of cases, for a very high number of cases, because there are a lot of chances of an even number of inputs being 1. In fact, half the possibilities are there that an even number of inputs will be 1. So that quite does not work. Okay. So that is where we will use this result, and this would kind of guarantee that with high probability there is exactly one which is 1. Okay. So this is roughly the, because that can be amplified. Okay, because this is a one sided error thing. So if it is greater than 1/4, so I will so basically what I will show is that I will use log square and random bits first to get error bound of 1/4, and now I will replicate this another r log n times. Okay, and that would bring down the error from 3/4 to less than 1/n to the power r. So that would give me from log square n, it would take it up to r log cube n, which is order log cube n. So those technicalities we will see now. So essentially, yeah, so this is what we will be showing now. Okay. So any questions about the statements or the setting? So then we will see that. So after we have proved everything, we will see how we can convert a probabilistic circuit to a deterministic circuit. Okay. And that is okay. So maybe I can mention that that is also easy. So what we will do is that we will simulate the circuit on all possible choices of random bits. Okay. So we will get a circuit which uses order log cube and random bits. So we will take 2 to the power log cube and many copies of that circuit. That size is still quasi polynomial, and now we know that for a majority of those circuits it should give the correct answer. Okay. So we will put a majority gate at the top, and whatever is the output of that majority gate will be the output. So that makes it deterministic. Okay. And because it is log cube n, 2 to the power log cube n is still quasi polynomial. So that blow up in size is still within what we can afford. So that is standard thing. Okay. So before getting into the proof of lemma 3, a couple of more points. Yeah. So as I said, let me just rephrase it. So first, approximate and then OR gates with depth 2 circuits of the form. So we have a parity, and then we have AND gates below it. Okay. So this is equivalent to a polynomial over GF2 of the form sigma pi. And one more thing that we will be using quite frequently is how we can squash the depth. That is, if we have, let's say, okay, let me use a notation over here, sigma pi S R. So essentially what this means is that so we have S terms and each term is a product of R literals or input, whatever. Okay, so these products are, so these AND gates have fan in at most R, and the parity gate at the top has fan in at most S. So now one more point. So suppose we have we have a polynomial which is of the form sigma pi, okay, where let us say this is some okay, some S1 T S2 R. Okay, how can I convert it to a polynomial of the form just sigma pi? So what is this? So essentially this means that, well, I have a product of some literals and I am summing them, and then again I am taking product of those and again I am summing them. Okay, if I have something of this form, how can I convert it to a polynomial of the form sigma pi? Okay. So if we just straightforward apply distributivity, okay, just by applying distributive law, if I just expand out the polynomial, how much will be the corresponding blow up in the fan in of the AND gate and the parity gate? How much will it be in terms of S1 T, S2 and R? So you can actually look, I mean, this is not difficult to see, you can just write it yourself. So the product gate will now have or the AND gate will now have fan in TR, and the parity gate will have fan in S1, let me just make sure, yeah, S1 into S2 to the power T. Okay. So if you expand it out, there will be now be a total of S1 into S2 to the power T terms, and each term will have TR many literals. Okay. So you can verify this quite easily. Yes, yes.
And so there are some literals which are.
So I mean, you can okay. So let me just give a small example. So suppose we have something like x1, x3 plus x4, x5. Okay. Now this is a sigma pi formula. Now I do this with another sigma pi formula. Let's say x2 plus x4. Okay. Now this is a sigma pi, sorry, pi sigma pi formula, and now again I have, let's say, something similar. Okay. Now what I will do is that I will just apply distributivity. Okay, I will just multiply and add accordingly, and I just spread it out to get it into sigma pi, and we know that here everything has at most R terms. The number of such terms is S2. These product has at most T terms, and the number of these terms is S1. So in terms of S1T, S2R, if I apply distributivity, I get it in this form. That's all. It's just straightforward verification.
So I said because there are two elements in each of these.
There are S2 elements in each of these. So when I multiply two of them, I will get 2 S2, right? Huh? If I multiply 2 of them, I will get S2 square, right? If I multiply 2 of them, I will get S2 square, right? So now I know I have a total of T of them. So it is S2 to the power T, and each one of them is contributing the same number. I have S1 of them. So therefore it is S1 into S2 to the power T. So, okay. So now we come to the proof of lemma 3. So let m be log of n. So for us, m will be ceiling of log n. So essentially the yeah. So basically, why is it log n? Because if I have to represent an index over here, that index, the representation of that index takes log m bits, right? And that is essentially S for us. Okay, so as I said, S will be all those indices for which the OR gate, I mean, which gives an input 1 to the OR gate. Okay, so that is why m is log n for us. We will build, wait here, build a circuit, let me call it C1 first, which takes as input x, and it takes random bits w, in fact random strings w1 up to wm. Okay, so w1 up to wm are chosen randomly, and each of them by themselves are strings of length m. Okay. So therefore, this circuit is taking how many bits as input? So it is taking n plus m square bits as inputs. Okay. So x has n bits and all these will have m square bits. So in fact, let me write this as x1 x equal to x1 up to xn. Okay, so these are the bits. Now for any a belonging to n, a can be represented as a log m bit string a1, or not log m, it is log n. So just use m over here, can be represented as a m bit string a1 up to am. Okay, and we define w I or a dot wi to be the sum of ai w I j, sorry, not ai, a j w I j, j going from 1 to m. Okay. So yeah, so this is again just standard. So a is a vector, w is a vector. Here I am just doing the dot product modulo 2, and as I said, everything is modulo 2. Okay, although I am writing these as sums, everything that we are doing is modulo 2. So this is just a standard dot product. And what is a? So any number between 1 and n, I can just think of it as a m bit string, and these m bit string is basically these bits a1 up to am. That is the notation that we will use. So now we will build this probabilistic circuit.